point Q. Okay, point Q is a certain arbitrary point that we pick, and we want to see what is going on in point Q. So at the top, right, we have a force P acting on the structure. At a certain point Q, right, so this is our deformation pattern, right, and I'm going to sketch our our axis, okay, our shaft X or our structure axis. We know that we have a certain distance over here, which is our Y. Okay. So at point Q, what is going on is we have a reaction load, right, in the vertical direction, right, and we have to have a counter moment acting in this direction. Okay, and that counter moment is equal to minus Py. Let me write better. So we have a counter moment over here, and this counter moment, okay, this counter moment M at point Q is equal to minus Py. Why minus? Because it's going in a clockwise direction. Okay. Okay, so we are still looking at point Q. Okay. Now, the next part is where I think you guys are better in math than me. Okay. The next part is we are going to derive a series of math. Okay. Now, what are we trying to show down there? What are we trying to prove? Okay. At the end of the day, I'll show you the final form of this formula. Okay. I'll write to you the final form of this formula. The final form of this formula is stress critical is equal to pi squared over L squared, okay, EI over A. Okay, that is the what? Critical squares. Okay. If we look at what we have, so this is what we are trying to derive. Right? Now, if we were to go back to our previous equation, where stiffness, or if we look at our previous equation where deflection is equal to PL over AE, and we know that stress for this case is P divided by A. Now this is under non-buckling situation. Right? Then we will ask ourselves, how come in buckling the equation is so much more what? Complex. Yes or no? You have, where did pi squared come in now? Right? You could understand why we have E, why we have I, right? Why we have second moment of area is more or less explainable, because the failure is similar to what? The deflection is similar to what? Bending moment, right? Then why are we doing an L squared at the denominator multiplied by A or divided by A? So I'm trying to show you what is going on. How did they, without those days of television, able to derive a formula like this? And if I show you the procedure, how this has been derived, you will say, is that it? Right? And it's I'll call this beautiful if you ask me to describe it, okay? Okay. So now, where are we going to start? Okay. So we're going to start that the moment about point Q is equal to minus Py. That we know already, right? So we did derive this, right? This is equal to minus Py over here. We know that, okay? So the next one, we are going to apply the elastic curve equation to relate bending moment to deflection. Okay. I hope probably you guys were taught this in math. Were you all taught this in math, elastic curve theory? No? Okay. If no, we are just going to apply the theory. Okay. So the elastic curve theory relate moment is equal to EI, Young's modulus, multiplied by second moment of area, d squared y over dx squared. Okay. This is what we call the elastic curve equation. Okay. This is what we call the elastic curve equation, right? So now we know moment is equal to EI d squared y over x squared. So now if we write d squared y over dx squared, this is equal to m over EI. And our m over here, our moment, right, which is equal to minus Py over EI. Okay. So from here, we are able to write this to be equal to d squared y over dx squared plus by Py over EI. And the whole thing is equal to 0. Okay. I could not remember what is this equation equal to. Did we write equation number 4, 5, 6, equation 7? I do apologize. This is our equation 7. So can you solve equation 7? It's straightforward for you guys, yes or no? Right? When do you all learn second order homogeneous equation? You all learn that already, yes or no? Recently, yes or no? Right? So if we look at the parent function, right? If we look at the parent function, we have d squared y over dx squared, right? Plus by a, right? dy over dx plus by b, y is equal to 0. This is the parent function. Okay. So what we're going to do now is we're going to let, all right, small p is equal to big P over EI. We're going to square root it. So this term, what you see over here, the P over EI, is this term over here. Okay. So therefore, equation 7 will become d squared y over dx squared plus by p squared, small p, okay, y is equal to 0. Okay. So now if we were to look at the general solution, can you all remember the general solution? So what is this? Is it 2 real roots, 2 repeated roots, or complex conjugate roots? Anyone? Any idea? Wait, when do you all learn second order differential equation homogeneous? last semester. You cheeky soul. This is not just important, no? Second order differential equation is critical for mechanical engineers, okay? If you are cracked in math, fine, like me, okay? I'm not the strongest in math compared to my sister, okay? But this second order equation is critical in a lot of mechanical engineering systems. Vibration, structure analysis you see now, okay? It's important, so don't forget it. Okay, if you forget, it's fine. I like honest people, okay? Not that you're trying to smoke me out. So the solution that we get, okay, so the general solution the general solution that we get, so what we have is two imaginary roots, okay, or we have, sorry, not two, but imaginary roots. I don't know math, what you all call that, maybe roots with the complex domain, right? Could you remember complex conjugate roots? Yes, you remember, there is hope. So what we have is y as a function of x is equal to e c1x, then we have a bracket c2 sine bx, okay, plus by c3 cos bx. Okay, we have it in this form, right? But because, right, our term down here, the c1 is equal to 0, y is equal to 0. This is because a is equal to 0 in our case. So if you look at our function, our a term down here, not this whole thing, apologize. The a term down here in our function, a is equal to what? 0 for our case. So we don't have the decaying term. Okay, we don't have a decaying term. So when we don't have the decaying term, we have e to the power of 0, right? C2 sine bx plus by c3 cos bx. Okay. So our final term over here we have is equal to c2 sine bx plus by c3 cos bx. Okay. So the general, therefore, I will write the final, we will write the general equation. So therefore, the general equation becomes y as a function of x is equal to a sine small p x, okay, plus b cos small p x. Okay, so this is our equation number 8. Okay, so what we are going to do next is we are going to impose, okay, a boundary condition right? We're going to impose boundary condition such that equation 8, okay, will be unique solution. Okay, I'm going to stop here for now. Come back at 10:30. We will carry on. Okay, so you can see for equation 8, it's still just a general solution. It's not unique yet, right? It's unique when we impose our boundary condition and then we derive the rules of or the formulas for buckling. I'll see you guys later.